Understanding digital logic. Digital logic is the foundation of all digital systems, including computers, smartphones, and other electronic devices. At its core, digital logic is a system of rules and operations that allow devices to perform complex tasks using only two states, on 1 and off 0. These states correspond to binary numbers, where 1 represents true or on, and 0 represents false or off. Digital logic is essential because it allows electronic circuits to make decisions, process data, and carry out computations. It's the backbone of all modern digital technology. Binary system and Boolean algebra. Digital logic relies on the binary system, a numbering system that uses only two digits, 0 and 1. This is different from the decimal system, which uses 10 digits, 0 and 9. Binary numbers are the language of digital systems, allowing for the representation of any numerical value or logical condition using combinations of zeros and ones. Boolean algebra is a mathematical system used to describe and manipulate logical statements. It's named after mathematician George Boole, who developed the theory. In Boolean algebra, the basic operations are and, or, and not. These operations are used to combine or modify binary values to produce a specific output. For example, AND operation gives a true result, 1, only if both inputs are true, 1 and 1. Or operation gives a true result if at least one input is true, 1 or 0, 1 or 1. Not operation inverts the input, turns 1 into 0 and 0 into 1. Logic gates. Logic gates are the physical manifestation of Boolean algebra in electronic circuits. They are the building blocks of digital systems, performing basic logical functions on one or more binary inputs to produce a single binary output. There are several types of logic gates. AND gate outputs 1 only when all inputs are 1. OR gate outputs 1 when at least one input is 1. NOT gate outputs the opposite of the input. NAND gate outputs 0 only when all inputs are 1. NOR gate outputs 1 only when all inputs are 0, not OR. XOR gate outputs 1 when the inputs are different. XNOR gate outputs 1 when the inputs are the same. These gates are combined in various ways to perform more complex operations and to create circuits like adders, multiplexers, flip-flops, and counters. Combinational and sequential logic digital logic circuits are categorized into two types: combinational logic and sequential logic. Combinational logic circuits produce an output based solely on the current inputs. The output is a direct function of the inputs, and there is no memory element involved. Examples include arithmetic operations like addition or subtraction, where the output is determined immediately by the input values. Sequential logic circuits, on the other hand, depend on both the current inputs and the history of past inputs. These circuits include memory elements like flip-flops or latches, which store information and allow the circuit to remember past states. This makes sequential logic essential for creating devices like counters, registers, and state machines. Real-life use cases. Digital logic is everywhere in our daily lives. One common example is the alarm clock. When setting the time for the alarm, the internal circuit uses digital logic to compare the current time with the set time. When they match, a logic circuit triggers the alarm. In computers, digital logic circuits are responsible for everything from basic arithmetic to complex decision-making processes. The central processing unit, CPU, of a computer uses digital logic to execute instructions, perform calculations, and control the flow of data. In traffic light systems, digital logic ensures that lights change in a specific sequence based on timers and sensors. The system uses combinational and sequential logic to manage the timing and the transitions between green, yellow, and red lights. Conclusion. Digital logic is the backbone of all modern electronics, allowing devices to process information, make decisions, and perform tasks. By understanding binary systems, Boolean algebra, logic gates, and the difference between combinational and sequential logic, we can appreciate how simple ones and zeros can power the incredibly complex digital world we live in. The concepts of digital logic not only govern how our devices operate, but also form the foundation for innovation in computing, telecommunications, and automated systems.